Okay, so but there can be the round of errors, right? Suppose you are solving this system in using one of the method in the computers, right? So the matrix A is given to you, and say instead of the vector B, we supplied some perturbation of B, right? There can be some round of error in the vector B, right? So let's try to see how does the solution change in that case, like in what parameters the solution is going to depend. So if you're, suppose I'm having very small perturbation of the vector B, which is given to me. So what will happen to the corresponding solution? So if I call the corresponding solution to be x tilde, so basically x tilde is satisfying the system. So how does this relate to the exact solution, and what is the relative error, right? So let's try to understand that. So we have a given system. The actual system is Ax is equal to B.
X equals to B.
Okay, and suppose I perturb the B a little bit. So when I say perturbation, it can be a round of error. It can be, say, you're just because of the machine error or because of the round of error, you can have some perturbation of the B, right? And the correspondingly, the solution what I get, let's denote it by x tilde. Okay, and let's call this vector as B tilde. Okay. And I want to understand that if my change in the B is small, that is, if B and B tilde is pretty close, then can we say that the solution x and x tilde, they're also going to be close or not, right? So this is going to depend on the condition number. So let me state this theorem, and then we will understand that what is the importance of the condition number. So let's take an invertible matrix A. Let A be an invertible matrix. Invertible, let's take it to be n by n matrix, and let x and x tilde, they are the solutions of the linear systems which are Ax is equal to B and Ax tilde is equal to B tilde. Okay, respectively. Okay, and here B and B tilde are the given vectors. So I'm going to obtain the result for any B tilde. In particular, when we have a B tilde as B plus R, we will be able to derive that how things are going to look like in that case. So then we can prove that if I consider the relative error in X, that is this factor, this is less than equal to the relative error in the right hand side vector B times norm of A into norm of A inverse. Okay, and here X, so here you can observe that there are two kinds of norm. When I write norms on the vector, this is a vector norm, and when I'm writing the norms on the matrices, this is a matrix norm. Okay, so this is for a fixed vector norm and the matrix norm, which is subordinate to this vector norm. Okay, so let's try to prove this result. So let's call it 1. So proof is not difficult. So it just follows with a quick realization that we have the invertibility of the matrix A, right? So we have X is the solution of this system, and then X tilde is the solution of this system, right? and A is given to be invertible. Right? So if I subtract these two equations, I will get ax minus x tilde. This is equal to b minus b tilde. Okay? And since A is invertible, I can get x minus x tilde as, if I multiply A inverse to b minus b tilde, this is going to be my x minus x tilde. Right? And from here, if I take the norm of this, so this is going to be the norm of A inverse b minus b tilde. So this will be less than equal to, so this is a norm of the property of the matrix norm, that this is going to be less than equal to norm of A into norm of the vector b minus b tilde. Okay?
Yes, ma'am.
So now let's also see so what we have to analyze is the relative error, right? So this means that I have got the control on the norm of x minus x tilde, and let's see how do we get the relative error. So note that we have b as, b is a into x, right? So
Yes.
from here the norm is this. Okay, so if you try to observe, I want to prove this relation, right? So norm of x is in the denominator here, right? So if I want to get that that 1 by norm of x is less than equal to something, this means that I have to get norm of x is greater than equal to something, right? Then the reciprocal will be less than equal to. So that's what I will try to realize from here, that if I again use the property of the matrix norm, this is less than equal to norm of A into norm of x. So from here, I can observe that norm of x is greater than equal to norm of B divided by norm of A. So if we just try to combine these equation 2 and 3, so these inequalities, so I can observe that this factor divided by norm of x, so basically norm of x is greater than equal to this, so this will imply that 1 by norm of x is less than equal to norm of A divided by norm of B. So combining these two estimates, we will get that this factor is less than equal to norm of A into norm of A inverse into norm of B minus B tilde divided by norm of B. So this is what we wanted to prove. Now, what is the importance of this result? Let's try to focus on that. So this factor which we are seeing here, so there's a name for it. This is called the condition number of the matrix A, right? Now, why this factor is important? So you can observe that B, so if you try to see this factor, this is a relative error in the vector B, right? So suppose if we talk about the perturbation which you are talking about here, so B minus B tilde is nothing but R, right? So this is like a relative error in the vector B. When you perturb B to some B tilde, so this is what you will get as a relative error. Right? So what it says that if your B is very close to B tilde, so this relative error in the B is going to be very small, right? But the corresponding error in the solution is not just depending on this factor, it is also depending on this factor, right? Which is called the condition number of the matrix A. So even if your B is very close to B tilde, but if your condition number of the matrix is large, then the solution can be far away. That is, the X might not be close to the X tilde. Okay, so let's first define the condition number and then try to make some observations using this equation, which is 1. Okay, so this factor which we have just obtained, so this is called condition number. So let's define formally what is a condition number of a matrix. So suppose I have a n by n invertible matrix. then the condition number of the matrix A is defined by, so this product, that is a norm of A into norm of A inverse. So since A is invertible, A inverse exists. So if you take the product of the norm of A and norm of A inverse, this is called the condition number of A. And the notation which we used to denote the condition of A is this. So COND is basically, we are meaning the condition number of the matrix A. Okay, so let's give it a question number 4. So one property of the condition number is that if you try to observe, so this is remark. So we know that A and A inverse, if we take a product of them, we are going to get an identity matrix, right? So
yes, ma'am.
Yeah, so this will give you some, so you can basically extract the lower bound on the condition number using this relation. So if I take the norm both sides, so norm of I, this is going to be norm of A into A inverse, right? And now this is less than equal to norm of A into norm of A inverse. This is a property of the norm again, right? And this is a condition number of matrix A, right? Now, whichever norm you take for the identity matrix, like we have seen, there are various norms. You can define the row norm, column norm, Euclidean norm, right? So whichever norm you take for the identity matrix, you can find out that its norm is going to be always greater than equal to 1. Okay? So what we have observed from here, that the condition number of the matrix A is always greater than equal to 1. Okay, so now if I look back this relation, so this is, I think we call the 1. Yeah, so if you look back this relation 1, what we can extract from here? So let's make a remark 2. So from here, I can basically extract the information that if my relative error in the B is small, in that case as well, the relative error in the solution can be large if the condition number of the matrix is large. Okay, so let me write this as a remark. So this is a theorem 1. So from theorem 1, it is clear that if the condition number of the matrix A is, so the best possible case I can have that when this is close to 1. Okay, so we have observed that this is always greater than equal to 1. So if the condition number is close to 1, then of course, if the difference in the B and B tilde, that is if the relative error is small, then your relative error in the solution is also going to be small, right? But if your condition number is large, it will affect the, you can have the X in X tilde very far away. So it is clear that if the condition number of the matrix A is close to 1, then the relative error in the solution will be smaller whenever the relative error in the right hand side vector is small. Whenever the relative error in the right hand side vector B is small, right? On the other hand, if you have condition number of the matrix A is large, if the conditional number of A is large, then the relative error in solution so this could be large. This would be very large, even if the relative error in the right-hand side vector is small.
Yeah.
Okay, so let's take one example to observe this phenomena. So I'm just taking the matrix A as five, 7, 7, 10, right? And take the vector B as 0.7 and 1. So basically, I'm interested in solving this system. 5x1 plus 7x2. This is equal to 0.7, and 7x1 plus 10x2. This is equal to 1. So we can solve this system. So this is a 2x2 system. You can find the solution, and the solution is, so I'm writing it directly. You can verify it. So solution is going to be x1 will be 0 and x2 is going to be 0.1. Okay, that is, if I denote x as x1, x2, this is the vector 0, 0.1. Okay, now let's just perturb the vector b. So I'm going to consider the perturbed system as so the first b1 I'm going to perturb it to by 0.01, that is I'm going to take 0.69. Okay, and b2 I'm going to again perturb it with 0.01, so I'm going to take 1.01. Okay, so there's a small change from the vector b, what we have here, to the vector b, what we are having in this new system. So here the b tilde, if I try to just put the things analogous to the theorem statement, so here b tilde is 0.69, 1.0. Okay, so now the corresponding solution, so let's denote it by tilde because we denoted by the x tilde there, right? So you can find the solution. So x1 tilde is going to be minus 0.17, and x2 tilde is going to be 0.22. Okay, so this is a 2x2 system, so you can directly solve it. So this is what you will get as a solution. So basically x tilde I have it as minus 0.17 and 0.22. Okay, so now let's try to observe what is the relative error in the solution. So the relative error in the solutions So let's name the equations. So this is 5 and this is 6. So the solutions of 5 and 6 is, so this is going to be, so let's fix the norm. So I'm taking the norm to be vector norm as the Allen treaty norm, so that we can easily just take the maximum, and that will give me the value of these norms, right? So if you just find it out, so here you can observe that so when you will take the difference x minus x tilde, you will get it 0.07 and 0.12. So you have to take a maximum of both, and then you have to divide it by the norm of x. So norm of x you can observe from here, this is going to be 0.1, right? And norm of x minus x tilde is 0.17, and you divide by the 0.1, so you'll get 1.7. Okay. Now, let's also observe what is a relative error in the right-hand side vector. So we have that the difference in b minus b tilde is 0.01, right? And norm of b tilde, if you will compute, so b is this. So 1 is going, so norm of b tilde, sorry, norm of b is nothing but 1. And b minus b tilde norm is going to be 0.01. So this is going to be 0.01, right? So you can see that this error, that is the relative error in the solution, this is
Bigger.
as compared to
Right side vector.
the relative error in the right hand side vector, right? This is what we are comparing as in the theorem 1. So which is high as compared to the relative error in the right hand side vector, which is given by this, right? Now the reason could, now we know that what could be the reason for this phenomena, right? We know that if so we are having this quantity to be small, but still this quantity is large, right? This means that only possibility is that the condition number of the matrix is going to be large, right? So you can find out the condition number of this matrix A here. So we have this matrix. So you compute the norm of A. Okay, you can compute either norm of A infinity or norm of A1. Both will give the same value. And then you also compute the norm of the A inverse, and then you multiply this will give you the condition number of the matrix A. Okay, so this you find it. So I'm writing directly what I will get as an output. So we get this as 289. Okay, so you can see that the condition number of the matrix is very large. So what we are expecting is that it should be close to 1, right? But you can see that this is a large number here. Okay, so this is the reason that even though the relative error in this right hand side vector is small, that is, you have a very small perturbation of the right hand side vector, but the two solutions are far away. Okay, so the reason here is that the condition number of the matrix A is 289, right? So therefore, the magnification of the relative error is expected. Okay, so the message from this result is that that your matrix has to be well behaved. Well behaved meaning this is also called the well conditioned, right? To have the So suppose you are going to solve the system using the computer, right? In the computer, you always have the machine errors, right? And if your if your matrix A is sensitive to that machine error, meaning that if it is condition number is large, so it's whatever the solution you're going to get as an output, you might not. I mean, it might not be the close to the exact solution because with the same reason that your error is going to depend on the condition number of the matrix. Okay, so one has to always check that whether the matrix is well behaved or not. Okay, so based on that, whether your condition number is large or is small, we call it as a ill-conditioned matrix or the well-conditioned matrix. So let me just define it. A matrix with a large condition number is said to be ill-conditioned matrix. And a matrix with a small condition number is said to be well-conditioned. So these terminology, ill-conditioned and the well-conditioned, they can also be used with respect to the linear systems. So for example, sorry, what had happened? Am I audible?
Yeah.
Okay, and I hope you guys can see the screen as well, right? I think the call was dropped. So, okay, so what I was telling that that if we see the definition of the condition number, that depends on the choice of the norm. So the definition, let's give a definition number. Okay, the 4 we have given here. The definition 4 of the condition number of A, this depends on the choice of the norm. So just to be like, if I say just the condition number of the matrix A, now you might think that, okay, which norm I have to use, right? So just to avoid that, that ambiguity, one use this another definition of the condition number. So I'm denoting it with the star here. So you compute this factor, that is, you take the compute the eigenvalues of the matrix A and take the ratio of the maximum eigenvalue and minimum eigenvalue. So this lambda here belongs to the sigma A, and lambda here belongs to the sigma A. Where sigma A denotes the set of all eigenvalues of the matrix A, right? So this is another measure which is used to compute the condition number. So I'm not telling that these two factors, this condition number and the definition which we have seen before, those are same. So one can prove that this is always, so let me write here. So this factor here, which we have, that is a norm of A into A inverse, this is always greater than equal to this factor, okay? So, but one can prove that they both are very close, okay? So this basically gives you a good idea about the condition number of the matrix A. And this, you can see that this is independent of the norm. Once you have found the eigenvalues, you just have to take the ratio of the maximum and the minimum eigenvalues in the magnitude, okay? All right, so with that, I think this is all on the direct methods. Now let's move on to the iterative methods. So now, first of all, what is the need of the iterative methods? We have already learned some methods to find the solution of the linear systems, right? Then why we have to learn some other methods? So if we have A as an n by n matrix, and if you're solving Ax is equal to B, suppose you use the Gauss elimination. And now you try to count the number of operations which you are performing in finding the solution, like you reduce it to a system Ux is equal to G, right? Where U is an upper triangular matrix, and you solve this, right? So number of operations, if you try to count, they are multiple of n cube. That is your complexity, which we name it as we call it as a complexity of the system. So this is of order n cube, okay? Which I mean here that if you count the total number of operations which you are performing, that you first of all you multiply with the multipliers, right? And then after multiplying with the multipliers, you just suitably multiply with the coefficient and then subtract it with the different equations. So all these operations which we are performing here, multiplication, addition, subtraction, if you try to count total how many operations you are performing, they are going to be a constant multiple of n cube, okay? Now, if your n is very large, you can imagine that how many number of operations you will be performing to find the solution using the direct methods, okay? For that reason, we are going to look for the alternative methods for which we will have a less number of operations, so that, when my n is very large, I don't have to do these, perform like n cube types of operation to solve a system, right? So these iterative methods which we are going to see, they will have the complexity of order n squared. So that's, which is much less than the complexity of the direct methods. So the first method which we are going to see in the iterative method is the Gauss-Jacobi method. Or this is also simply called the Jacobi method. So to understand this, what this method does, so let's first take the general system, linear system. So I'm taking an n by n system here. So which is a11 x1 plus a12 x2 up to a1n xn. This equals b1. The second equation is a21 x1 plus a22 x2 up to a2n xn. This equals b2. Likewise, the last equation is going to be an1 x1 plus an2 x2, and the last term is going to be ann xn. This equals bn. So let's call it to be 1. So basically, in the matrix form, this is ax is equal to b, where the a is the coefficient matrix here and b is the right hand side vector here. So the one assumption which I'm going to take here is that my diagonal elements of this matrix A are non-zero. That is, I'm assuming that aii, they are not equal to 0 for all I. You'll see that why I need this assumption just in a moment. Okay, so before really going into what this method is, let's just do a little one step here on the system itself. So what I'm going to do from the first equation here, so let's call it E1, E2 up to En. So from E1, I'm going to solve for the X1. Okay, and then from E2, I'm going to solve for the X2. Likewise, from the En, I'm going to solve for the Xn. So basically, I'm just going to rewrite this system 1 here. The system 1 can be rewritten as, so from the first equation, that is E1, I'm solving for X1. So I will have, I'm taking all the other variables to the to the right hand side and then divide by the A1. So I will have X1 as B1 divided by A11 minus A12 divided by A11 X2 minus A13 divided by A11 X3, and the last term is going to be here A1n divided by A11 Xn. Okay, now from the second equation, I'm going to solve for the X2. So I will have X2 as B2 divided by A22 minus A21 divided by A22 times X1 minus A23 divided by A22 X3, and this will go up to minus A2n divided by A22 into Xn. Okay, and I repeat this procedure. That is, I'm going to solve for the X3 from the third equation. Likewise, from the last equation, I'm going to solve for the Xn. So I'll have Xn as Bn divided by Ann minus An1 divided by Ann X1 minus An2 divided by Ann X2. And the last term is going to be Ann minus 1 divided by Ann Xn minus 1. Okay, so if you just try to see that what this system is in the matrix form, so in the right hand side you can see that you have a vector x, right? If I try to write down this new system, let's call it 2 in the matrix form. So in the right hand side, in the left hand side we have the vector x, right? And here if I define this matrix B as, so this is going to be 0 minus A12 divided by A11 minus A13 divided by A11 up to minus A1n divided by A1n. Now here this is going to be minus A21 divided by A22, 0, minus A23 divided by A22 up to minus A2n divided by A22. And the last row of this matrix, if I define it as minus an1 divided by ann into, sorry, and minus an2 divided by ann, and this goes up to, so the last element will be 0, second last element will be minus an and minus 1 divided by an. So if I call this matrix as B and a new vector, let's define it as C, which is B1 divided by A11, B2 divided by A22. Likewise, the last element is going to be Bn divided by Ann. So then I can write down the system 2 in this form. So this is like Bx plus C. So I hope you can see it, right? That if we write the matrix form, so I'm just taking out the, you can see what all the coefficient which are multiple of like the egg size here, right? So that I'm collecting it in the matrix B, and these are, I'm collecting it in the vector C. Okay. So this is the form which we are going to use to get the numerical method. Okay. And as I said that now we are seeing the iterative methods. So what we are expecting in the iterative method? So we are aiming to find the approximate solution of the exact solution X, right? So we will be forming a iterative sequence. So first we will find, say, X1, right? Then we will use this X1 to compute X2. So basically we'll be finding the iterative sequence, and the sequence we will expect that this converges to the exact solution X. So now let's understand that what this Gauss-Jacobi method is. So as I said that since it is a iterative method, so I'm going to require an initial guess. Okay, so let's take the initial guess to be so x1, which is nothing but I'm denoting it by x1 1, x2 1 up to xn1 transpose. This is any initial guess of the solution vector X. Which is x1, x2 up to xn. Okay, so we know the initial guess now. So using this initial guess, we will be computing the first iterate, and then we will just we will reiterate that to get an iterative sequence. Okay, so let's see that how I'm going to use this initial guess to compute the first iterate. So I'm directly using this system. So what we have got here, this 2. Okay, so note that I already have this information about the first iterate, right? So what I'm going to do here, I want to compute the new iterate, say x1, 2 I want to compute. So I'll just, in the right hand side, I'll just use the initial guess here, and then I'll compute the first iterate. So basically I'm using the system 2. So the second iteration is, so this is the first iteration, that is the initial guess we have taken. So we are going to define the second iteration as, so I'm using the system 2. So I want to compute x1, 2. So what I'll do, I'll just use the known factors. So I'm going to have B1 divided by A11 minus A12 divided by A11, and now x2, 1 I'm going to use, minus this up, this goes up to A1n divided by A11 xn 1. Okay, so in the right hand side, if you see that I have used all the xi's which are present, I've used the initial gas for them, right? So likewise, we can compute all the components of the second iterate. So x2 is going to be, so here in this, I'm just using this equation again. So this is going to be B2 divided by A22 minus A21 divided by A22 times x1 minus, so next term will be A21, so this will be A23 divided by A22 x31, and the last term is going to be A2n divided by A22 to xn1. Okay, so likewise we are going to generate the second iteration. So the last component of the second iteration is going to be Bn divided by Ann minus An1 divided by Ann into x1, and the last term here is going to be An minus 1 divided by Ann xn minus 1 1. Okay, so knowing the x1, that is the first iteration, we computed the second iteration using this. Now you repeat this procedure. Once we have got the second iteration, you use this to compute the third iteration with the same arguments. So meaning that I'm going to write the general iterate now. Similarly, knowing the kth iteration, so let's denote it by xk, which is having the components as x1k, x2k up to xnk. We can compute the k plus 1th iteration as, so k plus 1th iteration, this is given by, so the first component of the k plus 1th iteration is b1 divided by a11 minus a12 divided by a11 x2 kth iteration, and the last term is going to be a1n divided by a11 and xn's nth component of the kth iteration. Okay, x2 k plus 1 is going to be b2 divided by a22 minus a21 divided by a22 x1 k, and with the last term as a2n divided by ann xnk. And the last component of the kth iteration is going to be bn divided by ann minus an1 divided by ann x1k, and this goes up to ann minus 1 divided by ann into xn minus 1th component of the kth iteration. Okay, or if I want to write it in the, we can just write it in the short form using the summations. So if I say I want to write the ith component of the k plus 1th iteration, so what it is going to be, so you can see that you have the factors, like in the x1 you have the a11 in the denominator to each of the term, right? So in the x2 you have the a22 in the denominator in each of the term. So in xi, I'm going to have the aii in the denominator. So I'm taking it out. And then it is going to be bi minus. And if you try to observe what we have the terms as in the right hand side. So I'm computing the xn. So other than the xn, you have all the components here, x1 up to xn minus 1, right? So I'm going to compute xi. So other than the ith component, I will have all the components here, and this is going to be aij, xj, ith iteration, and j is going to vary from 1 to n, and j is not equal to I. Okay, so this is what I have written these terms in the form of this summation. And this is going to be true for each I from 1 to n. Okay, so let's give this a equation number. This is C. This is 4. Or in the matrix form if you want to write, because we have already written this form here, right? 3. So you can see that I can directly write down the matrix form of this iterative sequence. So k plus 1th iterate is going to be with the same matrix B which we have defined, B times kth iterate plus C. Right? So B is the same matrix which is defined here. So let me just call this as a star. So where B and C are defined in star. Okay, so this is how basically we are computing the iterates. So you start with the initial iterate, say k is equal to 1, and then you compute the x2, x3 using this relation. All right. Let's name this as 5. So now we are obtaining a iterative sequence, right? So we have to understand what is happening to the error. That is how the error is reducing. Say if I'm going from kth iterate to the k plus 1th iterate, how the error is reducing, right? So we have to understand the error. So this is the error analysis of Jacobi method. So x is the exact solution and xk is the kth iterate. So the error I'm going to denote it by ek in the kth iterate. Okay, and I want to understand that this the relation between, say, first we will obtain a relation between ek and ek plus 1, and then we'll try to make some observations from there. So we know that the iterates are satisfying this equation 5, right? So and my exact solution is satisfying this equation 3, right? So if I just try to write down this equation 3, or basically the system 2 in the form of the sum, what do we have? So from equation 3, if we write xi, that is a ith component of the x, so it will be very similar, right? So you see the matrix B here. So this is nothing but we have aij's times the xj's plus bii. So it's going to be bi minus summation j equals 1 to n aij xj, and everything divided by AII. So let me keep the factor AII outside. Okay, and here J is not equal to I. Okay, so the exact solution satisfies this. And we have got the K plus 1 iteration is satisfying this 4, right? So from 4, we have that the K plus 1 iteration is summation here is Aij, Xj, but now these Xj's are from the Kth iteration. And this holds for each I. So what I'm going to do now, I'm simply going to subtract xi and xi k plus 1. So you can observe here that bi factor is sitting in both, so it will cancel out. So what I will get is that the summation j equals 1 to n, j is not equal to I, aij divided by aii, and x minus xj k. Okay, so this is so here I'm denoting it by ek, right? So if you observe, this is also a vector, right? So x is a vector, xk is a vector, so ek is also going to be a vector. So let me denote the component of this vector as e1, e2 up to en. That is, e1 is going to be x1 minus x1k, right? e2k is going to be x2 minus the kth, the second component of the kth equation, like that. Okay, that is, this is going to be my ei k plus 1. Okay, and this factor here is ej k. So what we have got is that ei k plus 1, this is minus summation j equals 1 to n, j is not equal to I, aij divided by aii into ej k. So if I take the absolute value both sides, so absolute value of this is going to be less than equal to, so I'll get rid of this minus sign here, and then I will have the absolute value of this into absolute value of this. Okay. So note that here we have the jth component of the kth iteration, right? So this factor will be less than equal to, so if we take the elementary norm of the vector ek, which is nothing but maximum of absolute value of all the components ei, right? So this will be always less than equal to the elementary norm. So I'm just going to use that here. So this will be less than equal to j equals 1 to n, j is not equal to I, aij divided by aii into elementary norm of ek. Okay. So further, if we set this factor, let's take it to be j equals 1 to n, j is not equal to I, aij divided by aii, and note that the summation is over all the j's, right? So now I'm going to take the maximum over all the i's. So I'm going to call this as mu. So then from this equation, what we can write that EI k plus 1, this is less than equal to, so note that this factor, which is the same factor here, so I'm just taking the maximum of mu is nothing but the maximum of all these factors, right? And here I'm having is for particular I. So this factor is always less than equal to the mu. So we have got this relation. So is it okay so far?
Yeah, ma'am.
So let me number it. This is 6. So now if you observe the left hand side, it is independent of, right hand side, it is independent of I, right? So I can take the maximum over all the i's. So this side, when I will take the maximum over all the i's, so this will become the L infinity norm of the ek plus 1. And in the right hand side, there's no I, so the value will remain the same. Okay, so let's number it as a equation number 7. So this is the relation which we have obtained between the error in the k plus 1th iterate and the error in the kth iterate. Okay, and you can clearly see that so the power of the ek, this is 1 here, right? So this is the convergence is linear here. Now what is the rate of convergence, which is mu here? So we can iterate this procedure. So this is going to be ek plus 1. Now for the convergence, we have to see whether ek plus 1 this is going to 0 or not. So for that, what I'm going to do that I'm going to use this relation 7 again for this term. So this will be less than equal to mu times L infinity norm of ek minus 1. And this procedure I'm going to repeat until I reach to the E0. So I'm going to get this as mu factor will be coming k times. So this is mu raised to power k. And the last term I'm going to get it as E0 L infinity. So when I say E0, this is like you're having the error in the initial guess. Okay. So from here, you can observe that if mu is strictly less than 1, then this term goes to 0 as k goes to infinity, right? That is the error goes to 0 as you increase the k if your mu is strictly less than 1. Okay, and this convergence is linear. Okay, so the requirement which turns out to be for the convergence is mu less than 1. And if you focus on what mu is, right? So if you want that mu has to be strictly less than 1, basically I am demanding that my matrix A is diagonally dominant, right? So for mu less than 1 to be true, so what we have to have? So if you try to observe this factor, so we are demanding that this is strictly less than 1. Okay, so basically we are demanding that summation of AIJs divided by AII. So I'm taking the AII to the other side. And this is j equals 1 to n. J is not equal to I. So this has to be true for all i's, right? So if we have this, mu is strictly good. Mu will be strictly less than 1. So, and this relation is basically telling you that the matrix A is diagonally dominant. So for mu less than 1 to be true, the matrix A has to be diagonally dominant. And what is the meaning of the diagonally dominant is this. So you can see that the diagonal elements, which are the AII, they are dominating the rest of the sums. Okay. So the conclusion from here is that if the matrix A is diagonally dominant, Then if you're going to use the Gauss-Jacobi method to find the iterative sequence, then the sequence is going to converge to, that is, the iterative sequence is going to converge to the exact solution. Okay. Now, if you just try to focus that we have the matrix representation here, right, of this method in the equation number 5. So if you focus on this parameter mu here, so this mu is nothing but, we have the matrix B, right? It's a elementary norm of this matrix B. That is the row norm of this matrix B. Okay, so let me just give this as a remark. So note that we have equation numbers. So this is 5. So in view of 5 and the B is given by star, you can observe that if you take the row norm of this matrix B, this is nothing but the mu, right? Because you see here, I'm having the sum over all the j is not equal to I, and in the matrix B, we know that the diagonal elements are 0. Okay, and then I'm taking the maximum over all the rows. So this is basically the row norm of the matrix B. So what we are having here, that if we want that error should go to 0, for that I need that mu is strictly less than 1. So which means that I'm demanding that the norm of the matrix B has to be strictly less than 1, right? So the error goes to 0 if we are having that mu, which is nothing but norm of B, this is strictly less than 1. Okay. So is it okay so far? Any doubts here? Any queries? All right, so if not, then in this method, if you try to count the number of operations, okay, so I'm not going to go into the details of this, but if you count that how many operations we are performing to finally get the solution up to the desired accuracy, it will be proportional to the n square. Okay, so it is much in terms of the number of operations, it is requiring very less number of operations as compared to the direct methods. Okay. Now here we have seen this relation. So mu is basically the rate of convergence here, right? So it was further suggested that we can make this method more faster in the sense that we can reduce the parameter which is coming here, because this is determining the convergence here, right? The faster it will go to 0, the faster the error will go to 0, right? So we can further reduce this factor here by doing a little modification in the method, which is the Gauss-Seidel method. So this is basically the modification of the Gauss-Jacobi method. Now let me explain this method. What is this method? And it's a, if you are clear with what we have done here, then it's just a simple modification of this method. So now what we do in the Gauss-Seidel method. So here what we are doing, suppose I'm computing x1 here, k plus 1th, the first component of the k plus 1th iteration, right? Then I'm using in the right hand side, I have x2, x3 up to xn, and I'm using all the information for the kth iteration, right? So this is okay because I don't know anything about, I'm computing the first iteration, so I have to use the existing information, which is fine. But when you could come to the x2, so I'm computing the k plus x2 of the k plus 1th iteration. So this is also requiring, I'm using x1, x2, sorry, x3 up to xn of the kth iteration, right? But note that I already have x1 from the k plus 1th iteration. So rather than using x1 here from the kth iteration, I can use very well the information which I have already computed, right? I can use here x1 from the k plus 1, right? And now when I will compute the x3, so I have already computed the x1 and x2 from the k plus 1th iteration, right? So to compute the x3, rather than using the x1 and x2 from the kth iteration, if you use it for the k plus 1th iteration, and if you repeat this process, then the method what we get is the Gauss-Seidel method. Okay, so the summary here in this method is that we use the information which we obtain in the calculation of each new component. Okay, so let's write down one of the iteration and try to understand it. So suppose we have the initial guess or initial approximation as x1, which is the vector x1, x2 up to xn with 1 in the superscript. Okay, and I want to compute the second iteration. So I'm going to compute the first component of the second iteration as before, as we have done in the Gauss-Jacobi. So this is x2, 1, and this will go up to a1n divided by a11 xn 1. Okay, so we have got x1 2. Now to compute x2 2, I'm going to use this x1 2. How? So we use this computed x1 2 to compute x2 2 as. So if I just follow what we have in the Gauss-Jacobi, this is what I will use. So this is V2 divided by A22, A21 divided by A22, X1. So I'm just writing first what we have in the Gauss-Jacobi. So this is what we have from the Gauss-Jacobi. Right? Now what changes I am doing here? Instead of using this 1 here, I'm using 2 because I have already computed this. Okay. So now once we have the x1 and x2 from the second iteration, I'm going to use both of them to compute the third component. So next, we use x1 and x2 from the second iteration to compute x3 from the second equation. And how do we do that? So this is going to be b3 divided by a33 minus a31 divided by a33. So in the Gauss-Jacobi, it was x1 1, right? Now instead I will use x1 2 because I already have that information. And then this will be a32 divided by a33 x2 2 because we have already computed that. And rest all the terms will remain as it is. So the last term is going to be a3n divided by a33, but this will be from the first iteration as well because I don't have the information other than the x1 and x2 from the second iteration, right? So if you repeat this process, the last iterate, the last component of the second iteration is going to be Bn divided by Ann minus An1 divided by Anm. And to compute xn, note that I've already computed x1, x2 up to xn minus 1 from the second iteration, right? So I can use all of them here. So I will use the 2, and the next term is An2 divided by Ann, x2, 2, and the last term is going to be An minus 1 divided by Ann, xn minus 1 from the second iteration. Okay, so from the Gauss-Jacobi method, if you try to compare, so these are the components which you are having different. So you are computing some information, getting some information after computation, and you're using that to compute the next iterate. Okay, so if I want to write the general iterate, that is the k plus 1th iterate. So ith component of k plus 1th iterate. So if you try to focus, suppose I'm computing x3, right? To compute the x3, x1 and x2 I'm using from the current iterate itself, and all the variables after the x3, that is x4 up to xn, they will be coming from the previous iterate, right? So if I want to compute xi, that is ith iterate of the k plus 1, I have already computed up to xi minus 1, right? So x1 to xi minus 1 I will be using from the current iterate, and then rest all the factors will be coming from the previous iterate. So this is going to be 1 divided by aii bi minus, so summation. So first I'm writing the first I minus 1. So they will be coming from the current iterate itself. So this is going to be xj k plus 1, and all the previous all the iterates after k plus 1, that is, sorry, I plus 1 to n, they are going to be from the previous iterate. Okay, and this is for each component I, where I is varying from 1 to n. So this is the Gauss-Seidel methods. All right. So the only difference here you can see from the Gauss-Jacobi method is that in the Gauss-Jacobi, this term was also coming from the previous iteration. That is, in place of k plus 1 here, I was having k here. But in the Gauss-Seidel, you are just you're computing this and using it. So basically, you already have the information up to 1 to I minus 1, and you use that here. So now we'll see that what is the error in this Gauss-Seidel method, but that we will see in the next lecture. So if you have any questions, you can ask now. So is the method clear that what we are really doing?
Yes, ma'am.
Okay. So see, there are two possibilities. Either I can just take one class on this Saturday and I can wrap the things up so that you have the next week free to prepare for the exams, or I can take the class on the Monday and then wrap it up. So as you guys are comfortable. So I can even take it on Saturday and then finish it. So what do you guys say? So there's one more class which I will be taking. So I can take it either on this Saturday, or I can take it on Monday. So what you guys are comfortable with?
We will inform you.
Sorry?
We will inform you after discussing in class.
Okay, so but inform should be by today itself, so that I plan the things accordingly. Okay.
Oh, okay, ma'am.
All right. Saturday, preferable time is morning 11 or 11:30. So just let me know if that suits you all. or otherwise
Okay.
I'll be on the usual time on Monday. Okay.
Okay, ma'am.
Then yeah, thank you.
Okay.